So we talked about using integrals to find areas and even volumes for very special cases where we're rotating regions about different axes, okay, or getting a very simplified sort of cross-sectional area. Well, we never discussed length of curves previously, okay, and so how do you find the actual length of curve? Not the area under the curve, but the actual length itself of the curve, okay? And to derive our result, I'm going to first give you a more broad arc length formula for parametric curve. Okay, and I do this because it's more intuitive. Okay, here you could see that you have the t-axis. Okay, and you could consider that time. So suppose, and you could view this as the trajectory of a particle moving, for example, just to gain some intuition. So suppose you have a particle that starts out at t1 over here. So this t1 here maps to the xy coordinate there. And then this t2 here maps to the xy coordinate there. So here you have x as a function of t, time, and y as a function of t. Okay, and it maps to the different times mapped to those two different points. Well, in that small time delta t, the particle moves to the right delta x and moves up delta y. So it's going around there. And we want the length of that small change, the length that it actually traveled, what the odometer would say. Well, that length is going to be approximated by a right triangle there. So you'll have the square root of delta x squared plus delta y squared. And we're going to multiply and divide by delta t squared to put our expression in this form. And then we're going to pull out that delta t squared out of the square root, and then it just becomes a delta t. And we take the limit as delta t goes to 0 to get derivatives. Okay. Now this formula is intuitive. You could think about dx dt as the velocity in the x component. You could think about dy dt as the velocity in the y component. And so when you square those and add them and then take the square, you're getting the speed. This looks like the speed. Well, the speed times the time gives you a small distance, and that's what's going on there. Okay? And so here's our general formula for a parametric curve. Okay? And we'll discuss this formula in the future when we talk about parametric equations. But for now, bear with me with that general formula, which at least gives us an intuition using time on how that formula works. Now suppose we want to find a curve that's described by a function f of x. So y is equal to f of x. Well, all we have to do is look at that formula there and just take t to equal x. Okay? In other words, we just are parameterizing x by x equals x, and parameterizing y by x. Okay, so both x and y get parameterized by x when we set t equal to x. And dy dt in this case will be equal to dy dx because dt equals dx if t equals x. Okay, and so our formula here will get dx over dx, which is just 1, and that's where that's coming from. And dy dt becomes a dy over dx. And that's equal to f prime of x. And so here's our final formula. If we want the arc length of a curve given as a function of x. What about if it was a curve given as a function of y? Well, you probably would have guessed. In this case, you take t to equal y, dt equals dy, and so dx dt will be dx over dy, or the derivative of the function g with respect to y. Okay, not x, but y. And again, looking back at that more general formula, here we'll have dy dt is just dy over dy, because again, t equals y, and so that's 1, and that's where that 1 is coming from. And dx over dt becomes dx over dy, and you get that final formula there. And this gives you the arc length, or the length of a curve, for a curve that's described as a function of y. So x is the output and the input is y. All right, so let's take a look at an example. Here we want to find the length of the curve y is equal to x to the 2/3 between x equals 0 and x equals 8. It's fair game to treat this as a function of x, okay, and just use this formula here. And that would sort of be the first guess. I mean, this does pass the vertical line rule, so it really is a function of x. The only issue is that if you take the derivative of x to the 2/3, you get 2/3 times x to the minus 1/3. And at x equals 0, this diverges, okay? And so it's unbounded, and so the derivative gives us problems, okay? But clearly that curve exists, and clearly its length is finite, okay? So that's just sort of an issue of how we parameterize the curve. Since our parameterization in x gives us an infinite derivative, why don't we just parameterize in y? And that's what we'll do here, just to avoid that sort of parameterization that gave us an unbounded derivative. And so solving for x in terms of y now, you'll get x is equal to 3/2. Instead of 0 to 8, we'll have y equals 0 to y equals 4. Okay? And so here is our function of y. We take the derivative of x with respect to y, and we get that right there. And we're not going to have any issues on the interval y equals 0 to y equals 4. Okay? And we'll plug in. We'll just plug in, chug, and use the formula there. And we end up with that expression here. Do a straightforward u substitution, and you get this final result, which is approximated by that. And that is the length of the curve, and that's yet another application of integration.